So in the last video, I showed you that every congruence class in Zn can be represented as the congruence classes 0, 1, all the way up to including the congruence class of n minus 1. So we have these nice representatives for each of our congruence classes modulo n. Now what I'd like to do is I'd like to define addition and multiplication on Zn. So let me tell you about addition and multiplication on Z first. So the operations of addition and multiplication on Z are what is called binary operators. What this means is that these are functions of the form integer cross integer in, so two integers as our input and one integer as our output. So for example, addition corresponds to the map taking integers a and b and setting it to a plus b, as we know how to do. So I want to define now how this induces addition and multiplication on our congruence classes. So here's a definition. Addition and multiplication on Zn are binary operators So they're binary operators, meaning that they're of the form Zn cross Zn goes back to Zn, and they're given by the following definition, the following formula. So if I take a congruence class A, and I want to add it to another congruence class B, these are what elements of Zn look like. So I'm taking two of these congruence classes as my inputs. When I add them together, I get the congruence class of A plus B. Similarly, if I take the congruence class of A and I want to multiply it by the congruence class of B, I'm going to get the congruence class of A times B, just as regular integers, right? A and B here are both integers, and so these operations, this operation in here is plus on just Z, and this is multiplication on just Z. And so you already know how to do those operations on the integers and then take the equivalence class, or rather the congruence class of that integer you get out. And so this is what I mean by the addition and the multiplication of integers, telling us how the addition and multiplication of congruence classes works. You want to add congruence classes, you have to add the integer representatives. But right now it looks like, so from these definitions suggest addition and multiplication of congruence classes depend on the choice of representative. right? So maybe it depends on A and it depends on B, because you have to use A and B in the arithmetic to figure out what congruence class you're going to get out from addition. However, in fact, it does not. It does not depend on the choice of representative. So I'm going to do an example of that first, and then I'm going to prove that doesn't depend on the choice of equivalence classes. That is, I'm going to prove that these operations are well defined. So, for example, take the congruence classes of 3 and 5 inside Z6. Since these are represented by different numbers that are less than 6 and greater than or equal to 0, I know they're distinct equivalence classes, but I can pick other representatives. So we can take other representatives. So why don't we take for 3, we'll add 6 to it, we'll get 9, so there's another representative. And for 5 I can add 6 and get 11, there's another representative for that equivalence class. And so addition does not depend on this choice of representatives. So let me show you why. If I take 3 and I add it to 5, what do I get? Well, the rule says I need to add those two numbers. 3 plus 5, I get the equivalence class of 8. And I could add or subtract 6 to that to get another representative. I'm going to subtract 6 to get it back down to 2 to put it in my range from 0 to n minus 1. Now, if I were to take this exact same summation, but write it slightly differently, so instead of 3, I'm going to be using 9, and instead of 5, I'm going to be using 11. Notice these are the exact same sets that I'm adding to the exact same set. I use the rule that was given. It says I should add those two things together. I should get 9 plus 11. I get the equivalence class of 20. And if I subtract 6 3 times from that, if I subtract 18 from 20, I see that 20 is congruent to 2 mod 6. So although I use different representatives, I'm getting the exact same set out, the congruence class of 2. Multiplication also doesn't depend. On the representative. So, what's our example for that? Well, let's take 3 multiplied by 5. I should multiply 3 and 5 as integers in order to compute which equivalence class I get as the output of this. That is, the congruence class of 3 and the congruence class of 5 should give me the congruence class of 15. Subtract 6 twice, so subtract 12, and I get down to the congruence class of 3. And if I do the exact same thing with the congruence classes 9 and 11, I'll get the congruence class 9 times the congruence class 11 is equal to 9 times 11 as integers, and then take the congruence class, and that's going to be 99. And I'm going to subtract multiples of 6, so I'm going to subtract 60. To get down to 39, I'm going to subtract 30, that's 5 times 6, and I'm going to get down to 9. I'm going to subtract another 6, and I'm going to get myself down to 3. And so, if you multiply using these representatives, you get the exact same set out as that. let's prove that this works in general now. Theorem. Addition and multiplication of congruence classes modulo n are well-defined. What that means is that the operation really doesn't depend on the choice of representative. Okay, so what's our proof? So this is a little bit more complicated than the other well-defined proofs, well-definedness proofs that we've done before. Instead of just taking two representatives that are equal and show that they go to the same element, that were constant on equivalence classes, this is a binary operation. And so we really have to take two different pairs and check that, so we have to take two different congruence classes and check that for those two congruence classes, if we use different representatives, we still get the same answer, just like in the example before. So I'm going to take two things that I want to add together and multiply. And so these are going to be in Zn. So take another pair of representatives. So representatives for A and B. So that is, we're going to take x and y integers and we're going to make sure that x and A are equivalent so that they represent the same equivalence classes. And similarly, y and b represent the same equivalence classes. We want to show that if we take A and add it to B, this is the same thing as x and adding it to y. Our strategy is to show that, well, so how would you figure out what this is? This is the congruence class of A plus B, right? And over here, this is the congruence class of x and y. So we want to show that A and B, A plus B, and x plus y are congruent. Modulo n. Okay, so how are we going to get to there from here? Well, the things that I know that A and x are congruent. What does that tell us? So we know that n divides x minus a, and as y gives the same equivalence class or the same congruence class as b, we have n divides y minus b. So something that we proved before was that if you divide two numbers, so if n divides one number and n divides another number, then n divides the sum. And rearranging this sum, I can write that as x plus y first, and then minus a plus b. And reading this off, this is one number minus another number, is divisible by n. That is saying that x plus y is congruent to a plus b modulo n. That's saying that these guys live in the same equivalence class, the same congruence class. So we can conclude by saying, if we wanted to add if we wanted to add the congruence class of a and b, to do that, we just have to add a and b and take the congruence class. However, a plus b is congruent to x plus y, so this is the same thing as the congruence class of x plus y. And finally, that's our definition for x plus y. So what we're saying is that addition does not depend on the choice of representatives. So we've shown that addition is well defined. For multiplication, I want you to take the same setup. So I'm going to take a, b, x, y, all integers with a and x being the same representatives for the same equivalence class, and likewise with b and y. Now this time we're going to have to get a little deeper. The deepest I went for addition was that I had to show that n was dividing x minus a. I'm going to go a little bit deeper with this and show even more information. You see, as these guys have the same equivalence class, we know that n divides x minus a. What does that really mean? And so, there's some integer q with x minus a is equal to q times n. So now I'm just down to some kind of formula in terms of integers. Similarly, because b is related to y, we can do the same kind of process. There is some integer. I'm going to call it q prime now. And this is going to be an integer with y minus b is q prime times n. Remember our goal. Is to show that if I take a times b as congruence classes, it's going to be a times b as integers, and take the congruence class, that's going to be x times y, and that's the congruence class of x times the congruence class of y. This is what we want to show. We haven't shown this yet. This is by definition, is the spot in the middle that we have to bridge. So we have to show that a times b is congruent to x x times y. So, alright, my camera cut out because I was going too long with that. So let me continue the proof. Here's the relevant information that was on the board from before. So we knew that x minus a is q times n for some integer q, and y minus b is q prime times n for some integer q prime. So what I'd like you to do is observe that we we can express a times b as, well, using that formula over there, we can move a to the right-hand side and the qn to the left-hand side. So we can express this as a is x minus qn. And similarly, rearranging the second formula over there, we have b is equal to, moving b to the right, q prime n to the left, y minus q prime n. Now I'm going to expand this out. So the first term I get is x times y, which is very important. That's what we're looking for. And the remainder is what? So I have x times y, I have minus x times q prime n. I have qn and y, so I get a minus y qn. And the last term I get is a plus q prime n squared. q prime n squared. So what I want to do with this is I want to move x times y over to the left-hand side. So I'm going to get a times b minus x times y is equal to, and now with the remaining stuff, all of this is divisible by n. So I can pull out a factor of n, and I'm left with minus xq minus y, xq prime minus yq plus q prime, and then an n. And so what am I saying? I'm saying that n divides ab minus xy so I'm saying that a times b is congruent to xy mod n. That's exactly what we wanted. So I can complete the proof using this. We conclude that the congruence class of A times the congruence class of B is equal to the congruence class of A times B. And now from this congruence here, we know that this is the exact same congruence class as the congruence class of X times Y. That's the congruence class of X times the congruence class of Y, just by definition of multiplication of congruence classes. But what we're really saying, so multiplication on Zn is well defined. So now that we have these really nice well-defined operations, these algebraic operations on our congruence classes, we're going to explore the properties that they have. So I'll write down some multiplication tables and addition tables for Zn next time, just for some examples. And then we'll also investigate the properties that they have. You'll find that a lot of the properties of addition and multiplication are very similar to the properties you know for addition and multiplication of real numbers, rational numbers, complex numbers, your polynomials. Anything that you know how to add and multiply will act very similarly to addition and multiplication here.